Hello, calculus students. Welcome to the lesson on taking integration with some trigonometric inverses. And the first thing that we'll talk about here is that to do well and to be able to master integration of trig inverses, you have to first be able to master derivative of trig inverses. So, I'm going to leave these 6 problems here for you to complete, and you need to memorize this. At some point, I will be quizzing you on this. Maybe not tomorrow, but further down the line, I will definitely be quizzing you on this. And you absolutely need to know this and commit it to memory in order to do the rest of this section well, in order to master the rest of these topics. It's always helpful to be able to do the proof of this, but if you're taking AP and you need to pass the exam, you have to memorize all of this. Okay, so I'm going to just continue on and just trust that you're going to do this work, and we'll worry about verifying that trust later. Alrighty, so we got a few examples here, and we're going to start with this first one that asks us to integrate dx over the square root of 9 minus x squared. And before we continue, it's worth taking a note that the derivative of all of these trig inverse function all have like 1 minus something x squared, or x squared minus 1, something of that format. So that's going to like inform the process that we're going to use here. Okay. So what I'm going to try to do is get this expression in the radical, or the radicand, to be like 1 minus something. So we can rewrite this as dx over the square root of 9 times 1 minus x squared over 9. Okay, so effectively what I've done is factored 9 out of this, and now I have this expression. And this expression here is good because it looks similar to some of the derivatives of the trig inverse function. I'm going to take this a step further. The square root of 9 is 3. So this is effectively what we have. Okay. And just keep going. Let's see, this is dx over 3, the square root 1 minus, and this term here, x squared over 9, we can change that to x over 3 quantity squared. Okay, and so now we have the form. Okay, and one of the nice things about calculus is that we can try to look for the right form, and that'll make the problem easier. So this is like some constant times the square root of 1 minus some expression squared. And from this point on, if you're comfortable, you could just go ahead and find the integral. If not, we'll do integration by substitution. So we're going to say that u is equal to x over 3. That means du dx is then equal to 1/3, and du is equal to 1/3 dx, which is what we have up here. So then our new integral then is 1 over the square root of 1 minus u squared, and then the 1/3 dx, well, that's just equal to du. Then we can take the integral of that, and this turns out as the antiderivative of this expression is sine inverse of u plus a constant. Okay. But remember that u is actually x over 3, and so that's our final answer for this one. Okay. So the main strategy here is for us to find a way to make this expression look like the form that we had for the derivative of the trig inverse functions. Okay, so this next one, we'll start with the same trick as what we had before. Just rewrite the integral as 1 over x, and then this 4x squared, it's a perfect squared 2x minus 1. 2x quantity squared minus 1 dx. And if we look at our list of options up here, you see that we have the closest thing that we have here is the derivative of secant inverse, but this has an x squared and then an x, whereas we have a 2x squared and then an x. So there's just a tiny little bit of work that needs to be done. So if somehow this expression out here could be be 2x, we could use the secant inverse function here. Well, it's not too difficult. All we have to do is just multiply the top and the bottom by 2, or by 2 over 2. And what we have now is then the integral of 2 over 2x root 2x quantity squared minus 1 dx. And then now this is just 2 times the secant inverse of 2x plus a constant. Oops, sorry. 2 times the secant inverse of 2x plus a constant. And again, this is so difficult unless you know these derivatives really, really well. You have to be able to recognize some of these forms. Otherwise, it's very difficult to figure out what the antiderivatives of these functions are. Okay. We'll look at one more. So this is an interesting one that involves some e to the x and e to the 2x here. So if we look at this, and I'm just kind of sketch out the strategy here before I dive into it further. This here actually resembles either the tangent inverse or the cotangent inverse. There's no negative here, so it looks a little bit more, it resembles the tangent inverse function a little bit more. So we're going to try to get this expression in our problem to follow this format. So this is a work in algebra, and then we apply the calculus rules, and it's actually pretty straightforward and simple from there. So this is equal to the integral of e to the 2x over, and I'm going to factor out the 4 here so that I can get this 1 plus 1/4 e to the 4x dx, which is equal to the integral of 1/4 times this expression. So now I have my constant pulled out, 1 plus 1/4 e to the 4x dx. And again, I want to get this thing to be like something squared. That's the goal. So to do that, it's been structured rather nicely for us to set this up. So this is e to the 2x over 1 plus the square root of 1/4 is just 1/2. E to the 4x is actually just e to the 2x squared. So we can say that this expression here is equal to this one. This is all times dx. Then apply some rules of substitution and let u equal e to the 2x. E 1/2 e to the 2x rather. So that means du dx is equal to the derivative of this, which is e to the 2x 1/2 times 2. Those go away. So now we have du is equal to e to the 2x times dx. E to the 2x times dx. Then make our substitution. And this down here becomes, I'm going to pull the 1/4 out to the front. E to the 2x dx is just the same thing as du. The expression in the denominator here is 1 plus this block here, which is just equal to u squared. So just to kind of hammer home the point, I can rewrite it this way, which is equal to 1/4 tan inverse of tan inverse of u plus a constant. But remember that u is this expression, So we have to back substitute, and we get 1/4 tan inverse of e to the 2x over 2, or e to the 2x times 1/2, plus a constant. And there you have it, a rather difficult and messy example, but it is totally doable if there's two things are true. One, you understand how integrals and substitutions work, and two, you are very, very fluid in working with inverse trig functions. Thank you for watching. Have a wonderful day.